Hi, in this video, we are going to continue our series of on vectors. So we started off the last class with basics of vectors. We also looked at the meaning of addition of vectors, collinearity, and coplanar vectors. Today, we are going to start with the topic of linear dependence. So first of all, I'll define what is a linear combination of vectors. So let's say we have vectors a1, a2 till an. These are vectors, and we have scalars L1, L2 to Ln, right? Then the quantity L1 A1 plus L2 A2 plus L3 A3 and so on till Ln An is called the linear combination of these vectors. Linear combination of these n vectors. So basically a linear combination is multiplying several vectors with scalar quantities and coming up with that sum. This quantity becomes the linear combination of these n vectors. Why is this important? Because we'll use the linear combination to talk about independent and dependent vectors. Okay. So what is a linearly dependent system of vectors? Linearly dependent set of vectors. So the vectors a1, a2 till an are said to be linearly dependent if there exist scalars, L1, L2 till Ln such that the linear combination of them L1 A1, L2 A2 vector plus L3 A3 vector so on till Ln An vector is equal to the zero vector where all the scalars are not equal to zero. All the scalars are not simultaneously zero. So what do I mean by this? So basically the idea is that if you can say that the linear combination of these vectors is equal to the zero vector and the scalars there are not all of them are not equal to zero, then you will say that the set of vectors is linearly dependent set, right? So it could be that a few of these scalars are zero, but not all of them can be zero simultaneously. If that condition is true, and you are still able to say that the linear combination of the vectors is a null vector, then you call this set of vectors a1, a2, an to be linearly dependent, right? Now, what is linearly independent? So, linear independent set basically is again the same thing. If the linear combination of these vectors ln an is equal to zero vector implies that L1 is equal to L2 is equal to Ln is equal to 0, then the set A1, A2 till An is a linearly independent set. So basically, if the linear combination of vectors becoming a zero vector means that all the scalars must be zero, we know that the set is a set of independent vectors, right? For example, a simple set of independent vectors is I vector, J vector, and K vector. These three vectors are independent to each other because anytime you have xi plus yj plus zk equal to 0 vector, that automatically means x is equal to y is equal to z is equal to 0. You cannot have x or y or z being non-zero and then still be able to add these vectors and make it 0 vector, right? So since all the scalars are simultaneously 0, if the linear combination of these three is equal to 0 vector, we call these three as an independent set, right? Now, if you have understood the definition of linear dependence and independence, I would like to point out certain other things. For example, collinear vectors are always linearly dependent. Why is that? If two vectors A and B are collinear, you can write A is equal to lambda B. And now we can write it like this: A plus minus lambda into B is equal to 0 vector. And you can see that the scalar L1 is 1 and L2 is minus lambda. And both of them are not 0. And you are able to add A and B is a linear combination and make it equal to the 0 vector. Therefore, we can say that A and B are linearly dependent. So that is the first idea. Collinear vectors are also linearly dependent. Then you can say coplanar vectors are also linearly dependent. So if I have three vectors A, B, C, which are coplanar, I know from the meaning of coplanar, which we discussed in the last video, that any one of them can be written as a combination of the other two, linear combination, right? So therefore, now you can write them as this: minus x times A plus minus y times B is equal to 0 vector. And you can see that the scalars are not all 0. 1 minus x minus y are the scalars. And since there is a 1 present, means all of them cannot be 0. So the set CAB, this is a linearly dependent set, right? So you should understand these two properties really well. Another point that I would like to make here is I, J, K are linearly independent because you can never combine them to make it 0 while ensuring that any of the scalars are non-zero. We already discussed this. Then any set of vectors, including the 0 vector, any set of vectors which has the 0 vector is always linearly dependent. So that is also another point. Also, excuse me, any four vectors, if you take any set of four vectors, are linearly dependent. So you can try to prove all of these statements. For example, if I want to prove this, I would assume four vectors A, B, C, D, and I will start off by saying, let's say two of them are collinear. If two of them are collinear, automatically this set will become linearly dependent because you can always write A is equal to lambda B. So you can write A plus minus lambda B plus 0C plus 0D is equal to 0 vector, right? And here minus lambda is non-zero and 1 is non-zero. So this is a linearly dependent set. So if any two of them are collinear, it becomes dependent. So we'll assume it is not collinear. So then you can take any three of them are coplanar, it will become again dependent because of the coplanar property. So finally you will say that assume they are non-coplanar, right? And then you can write the fourth vector in terms of the components of the other three. If they are non-coplanar vectors, the fourth vector can be written in terms of the other three, and you will be able to prove this property again. So that is the concept of linear dependence and independence. Let's look at a couple of examples now to understand this better. The question one is, if A, B, C are are non-coplanar, show that the vectors A plus 2B minus C, 2A minus 3B plus 2C, and 4A plus 3C plus B are linearly independent. Okay, so let's see how to do this. So one way to do it is to check the definition of linear independence. So we can say that if these three vectors are linearly independent, we have to prove that. So then we'll assume that x, y, z, let x, y, z be scalars such that x times a plus 2b minus c plus y times 2a minus 3b plus 2c plus z times 4a plus 3b, 3c plus b is equal to 0 vector. From here, I need to be able to show that if this is true, I need to prove that x is equal to y is equal to z is equal to 0. If this implies this, then we have our proof of linear independence, right? So from here, now I can write it like this. I can collect all the x, all the a terms together. So x plus 2y plus 4z times a plus 2x minus 3y plus z times b. And finally, we have minus x plus 2y plus 3z times c is equal to 0 vector, right? So if this is true and A, B, C are non-coplanar, then we must be able to write that the sum of three non-coplanar vectors will be 0 only if each of these vectors are 0 or the scalar parts here are 0. So what we can do here is say x plus 2y plus 4z is 0, 2x minus 3y plus z is 0, and minus x plus 2y plus 3z is 0. If you solve these two equations, these three equations, you will automatically get that x is equal to y is equal to z is equal to 0 is the only solution. Is the only solution. And because that is the only solution, that means that is the only way in which you can combine these vectors and make it equal to a 0 vector, which means that these vectors are linearly independent. Right? Okay, another question let's look at. Show that A is equal to I plus 2j plus 3k, B is equal to 2i plus j plus 3k, and C is equal to I plus k are linearly dependent. Okay, so if you have, they are linearly dependent on each other, then we can suppose that any two of them can be written in terms of the other. In terms of the other. So basically what I can do here is find out if they are linearly dependent. We have C can be written as x times A plus y times B. And then what you can write is here C will become x times I plus 2j plus 3k plus y times 2i plus j plus 3k. And from here we can see that this is becoming I plus k is equal to this. So you're getting x plus 2y I plus 2x plus y j plus 3x plus 3y k. So notice that now we have to have x plus 2y should be 1. You have 2x plus y should be 0. And 3x plus 3y is 1. Right? So solving this, we can easily see that x is minus 2y. And from there, if you put it in this equation, you get a minus 4y plus y. So y is 0 is coming. And if y is 0, okay, I'm making a mistake in calculations. 2x plus y is 0, x plus 2y is 1. So x is 1 minus 2y. And if you put that 1 minus 2y here, you get 2 minus 4y plus y is 0. So 3y is equal to 2. So y is 2 by 3. So x is becoming 1 minus 4 by 3. So minus 1 by 3. Right? So we are able to say that C is equal to minus 1 by 3a plus 2 by 3b. And therefore we are able to say that C plus a by 3 minus 2 by 3b is equal to 0. And that clearly shows that the scalars 1, 1 by 3 and minus 2 by 3 make the linear combination of these three vectors equal to the 0 vector, which means C, A, and B are linearly dependent. All of the constants are not 0, right? So therefore it becomes linearly dependent. We will see other ways in which you can check linear dependence and all. Right now, this is the way we proceed by the definition, right? Later, when we do triple product, we'll have a better way to check dependence and non-dependence also, right? So let's continue now. The next idea is the section formula in vectors. We have already seen this in basic coordinate geometry. The section formula for vectors says that if you have A and B are position vectors of points capital A and capital B, capital A and capital B, the position vector of the point P, which divides the line segment, AB in the ratio m is to n. Is basically we can say the P vector is equal to m times B plus n times A by m plus n. What is the meaning of this? So let's say this is A, this is B, this is my origin, this is my OA or A vector's position, this is my OB and B vector's position. I have to find the location of point P or position vector of P, where this is n is to n ratio, right? And I'm going to say that this vector OP is equal to this n times B plus n times A by m plus n. Now, how do we do this as a proof, right? So we want to prove this formula. So let's see how to do it. So I will draw the figure again. A, B, origin, P, m is to n ratio. This is A vector, this is B vector. And I want to find this P vector, right? So we know that AP by PB is equal to ratio m by n. So that means n times AP is equal to m times PB, right? And in terms of vectors, you can say n times AP vector will be equal to m times PB vector because both AP and PB vector have the same direction, are collinear. So we can write them like this. The directions are same, so we'll add a unit vector and we'll get this result, right? Okay, so now we can say n times, what is AP vector? AP vector is OP vector minus OA vector by simple addition rule in this triangle is equal to n times OP vector or OB vector minus OP vector, right? So from here we can write n times OP vector minus NA vector is equal to m times B vector minus MB OP vector. And now we can easily solve and say m plus n OP vector is equal to MB plus NA. And therefore OP vector or P vector for us is MB plus NA by m plus n. So the same logic of section formula also works in vectors. And using this, now we can figure out different situations where, for example, what is the bisector of a line segment? So if this is AB, the bisector of the line segment or the midpoint of the line segment's uh, position vector would be, if this position vector is A and this is B and this ratio is 1:1, then C's position vector is simply A plus B by 2. This is a simple application of your section formula for vectors, right? Similarly, we will be able to state the same properties that we saw in geometry. We can prove that medians of a triangle are concurrent. And we also know centroid divides the median, divides any median in the ratio 2:1. And from here, we'll get the position vector of the centroid. G vector is going to be A plus B plus C divided by 3, where A, B, and C are position vectors of the three vertices of the triangle. Right? So that is an idea that we are able to prove by section formula. You can do this yourself. It is not very difficult. Similarly, what we can do also is if you have a tetrahedron with 4 vertices and the position vectors of vertices are A, B, C, and D, then the position vector of the centroid of the tetrahedron will be A plus B plus C plus D whole divided by 4. So again, this is a fact that you should know, right? The next idea or the next point here, which is similar and comes by section formula, is that internal angle bisectors of a triangle are concurrent, and by angle bisector theorem, they divide the opposite side in the ratio of the two sides making the angle. Making the angle. So basically, we have a situation like this. Let's say you have A, B, C, and this line is an angle bisector. It divides this side in the ratio of C is to B. C is to B. If this side is C and this side is B. So what we can do is if the position vectors of the three sides are x1, x2, x3, right? The position vector of this point D would be Cx3 plus Bx2 by C plus B. C is a scalar, so C plus B here. This is the position vector of D. And another theorem here that you should know is that the in-center divides this line, the angle bisector. In-center divides angle bisector in the ratio. In this case, it will be B plus C is to A, right? So if my A vector was x1, I would say A times x1 plus B plus C times D divided by A plus B plus C. That would be my in-centers position. So I vector is going to be this. And finally, if you simplify this, the I vector's position vector will come out to be AX1 plus BX2 plus CX3, whole thing divided by A plus B plus C, where A, B, C are the sides of the triangle. So that is also a result that you should be aware of. Okay. Then another important idea, and this you should definitely remember, this is the theorem which says the unit vector bisecting the angle between two vectors A and B is given by A unit vector plus B unit vector by mod of A unit vector plus B unit vector. So what are we saying here? The unit vector between the two vectors A and B. So let's say this is my A vector and this is my B vector. So what we are saying is the angle bisector is going to be along this direction, right? So the reason that is so is because this is a congruent triangle. The distance of any point on the angular bisector with this is equal. This distance is equal to this distance. So if you have to find the vector of OP, vector along OP direction, right? That vector will be making equal angles. So the proof of this can be done easily if you do know cosine rule. So what I will say is vector along OP can be written as some scalar times A plus Y times B, right? Because OP vector is coplanar with A and B. Now all we have to do is find X and Y, right? So the way we do that is we know OP dot A is going to be same as OP dot B divided by mod OP and mod A, and here divided by mod OP and mod B. Why are we doing this? Because we are saying that the angles are equal here, theta and theta, because they are angle bisectors. So this is cos theta here between OP dot A and this is OP dot B, right? So when you do OP dot A here, what you will end up getting is x mod A square plus y A dot B divided by mod OP mod OP gets cancelled here. So divided by mod A is equal to, you are getting y mod B square plus x times A dot B divided by mod B, right? So from here, you will be able to show that x is equal to y is the only way this can happen. So how is that? Let's see why. We will be able to do cross multiplication, and we are getting x times mod A squared mod B plus y times A dot B times mod B is equal to y times mod A mod B squared plus x times mod A dot B, right? So now what we have is these are adding up, these are equal. So we can say mod A mod B common, and we have x times mod A minus y times mod B plus here A dot B common, and you have again y times mod B minus x times mod A is equal to 0, right? So what we have here is, you can take this factor as common from both, and if you do that, what you end up getting is the situation x mod A minus y mod B common factor, and you have mod A mod B minus A dot B, right? Since the angle between the vectors A and B is not equal to 0, this part cannot be equal to 0. So this part has to be equal to 0, which means x times mod A is equal to y times mod B, right? And what was x and y? X and y were the scalars along the angle bisector. We were saying angle bisector line was x times A plus y times B, right? So now we have a condition connecting the scalars x and y. You can see that x by y is equal to mod B by mod A, right? We can use that now to prove that if the two angles are equal, then x and y are in this ratio, and you will end up, if you want to get the unit vector, it will end up in this direction. So let's take an example to try to understand what is happening here. So what I will say is this: find a unit vector bisecting the angle between 2i plus j plus 2k and 3i plus 2j minus 6k, right? So what we can say here is, what is, let's call this as a vector, 2i plus j plus 2k. Mod of a is clearly 4 plus 4 plus 1, so 3. And b vector is 3i plus 2j minus 6k. So that is 36 plus 9, 45 plus 4, 49. So mod of b is 7, right? So the unit vectors in the direction of the two vectors, a vector and b vector, the unit vector in these directions are, a unit vector is 2 by 3i plus j by 3 plus 2 by 3k, and b unit vector is 3 by 7i plus 2 by 7j minus 6 by 7k. These are the unit vectors in these directions, right? So now let's find out a plus b by mod of a plus b, right? If you find out that vector, that should be in some direction like this. We can later prove that that vector is a bisector. So let's find out A plus B unit vector sum. What is that sum? That comes out to be 23 by 21 I minus J by 21 and minus 4 by 21 K. This is the sum of the two unit vectors. You can add it and check, right? And when you divide it by mod of A plus B unit vectors, mod of this vector A plus B is coming out to be 1 by 21 root over 546. So our required unit vector comes out to be required unit vector, which is A plus B divided by mod of A plus B, comes out to be 23I minus J minus 4K divided by root over 546. Now, what I can do is check whether this vector makes the same angle with A vector and B vectors. In order to prove that this vector is a bisector, I can check the dot product of this vector with A and this vector with B. When you do that, dot product with A, which was 2I minus J plus 2K. So the dot product would be 2 times 23 by root 546 minus 1 into minus 1. So plus 1 into root 546 and plus 2 into minus 4. So minus 8 into root 546. So you are getting 46 minus 8. So you're getting 38 plus 1, 39 by root 546. Right? The dot product here is coming out to be this. And what is the dot product of the same vector with B? The dot product with B, we have to check cos theta is same, cos theta 1 and cos theta 2. So you have to do A dot B by mod A mod B, right? So for our vectors, it is slightly annoying to check it. But if you check it, dot product with B vector was what? B vector was 3I plus 2J minus 6K. The dot product will be 3 into 23, 69 plus 2, so minus 2 and plus 24 by root 546. So you're getting 67 plus 24, so 91 by root 546. And we have to divide it by the mod of these two vectors to check the cos theta. So this vector I'll have to divide by 3 and this vector I'll have to divide by 7. So notice that you're getting the thing 13 and here also you're getting 13 by root 546. So cos theta 1 and cos theta 2 are both matching and they are 13 by root 546. So that shows us that our method of finding the bisector of any two vectors A and B will be along A vector plus B vector by mod of A vector plus B vector. This is the unit vector in the direction of the bisectors, and this is going to be super important later. So you should definitely remember this result. Okay. The next thing that I want to talk about today is the vector equation of a line and plane. So the first thing that we talk about here is the vector equation of a line parallel to the vector B and passing through the point whose position vector is A, is what? So basically, I want the locus of a point P or a point on the line P such that it passes through the vector A, let's say this is the origin. This is my unknown point. This is my known point. So the position vector here is A. This is my unknown point R. So this is going to be the point whose locus is going to be this straight line, right? And this straight line is parallel to B vector, right? So the segment here, this segment here can clearly be written as R minus A, right? This segment is supposed to be the segment on the straight line. And since R minus A is going to be parallel to B, I can write it as R minus A is equal to lambda times B. And from here I get R is equal to A plus lambda B. And this gives us the position vector of an unknown point on a line if that line passes through a point A vector and is parallel to a vector B, right? So that is my vector equation of a line. Here lambda is a scalar, okay? So understand the meaning of the thing. R vector is A plus lambda B. R vector is a general point on the line. A vector is a given point through which the line passes, through which the line passes, and B vector is the direction of the line because it is parallel to the line. Right? So in that situation, this becomes the line equation, right? Another way to say the same thing is this: the vector equation of the line passing through the points A and B, passing through the points A and B, whose position vectors are A vector and B vector, is R is equal to 1 minus T A vector plus T times B vector, where T is a scalar. Now understand where this is coming from. You have a segment AB. This is capital A, capital B. This is my origin. What we are saying is this is A vector, this is B vector. Any point on this line, a random point P here, could divide this line segment A and B in the ratio of T is to 1 minus T, right? And therefore, by section formula, the location R vector for P would be, by section formula, 1 minus T A plus T B divided by 1 minus T plus T. Therefore, R vector will be what? 1 minus T A plus T times B. So the R vector is a point, random point lying on the segment AB, right? And this is internal division that we right now considered. It could also have been external division, right? Okay, so this is something that you should be aware of. The next thing that we'll look at is the equation of a line passing through the point A, x1, y1, z1, and parallel to the vector and parallel to the vector B, which is given by L, M, and N components. This is actually same thing as before, A plus lambda B, but I want to write this in Cartesian form, and in Cartesian form you'll write it like this: x minus x1 by L is y minus y1 by M and is z minus z1 by N. Here L, M, and N show us the direction of the line, and the line passes through x1, y1, and z1, right? So you should be aware of this Cartesian form of the line equation also. Okay. Then the next point is vector equation of a plane. Vector equation of a plane passing through point A, whose position vector is A vector, and parallel to vectors and parallel to the vectors B and C. So what we can do here is the plane is parallel to the vectors B and C. So we can say that if a variable point P is in the plane, then the segment AP is in the plane, and obviously B and C are parallel to the plane. So what we can see is that the segments AP, B and C are coplanar, and AP will be R minus A, and B and C are given points. So we can say that R minus A can be written as lambda B plus mu C because they are coplanar. So we get R is equal to A plus lambda B plus mu C. Here R is a general point on the plane, and we are saying that this plane passes through the point A and is parallel to the vectors this B and C. Parallel to B and C. So notice the logic behind how we did this. We are saying that if a vector passes through a point, then we can construct a vector AP where P is a variable point in the plane. If the plane passes through a point, then AP line segment is in the plane, and also the plane is parallel to B and C directions. So basically we are saying AP, B and C are coplanar vectors, and we can write them in terms of each other. We can write R minus A as lambda times B and mu and C, right? So this is an important form that you should be aware of. This is the equation of a plane passing through a point parallel to two given vectors. Okay. Then the same thing can also be written in terms of plane passing through two points. Earlier we had one point and two vectors, right? Now we can be given 2 points A and B and parallel to vector C, right? In this case, these are the position vectors of these 2 points. The plane passes through these 2 points. So what I can say here is the equation of the plane would be R is equal to 1 minus S A vector plus S B vector plus T C vector, where S and T are scalars. How do I do that? Now that there are 2 points, I can take my variable point P and I can construct two vectors AP and PB. AP and PB are in the plane, and also C is parallel to the plane, right? So technically what we can say is AP, PB and C vector are coplanar. And AP vector is what? It is R minus A. PB vector is what? It is basically B minus, actually we can, in order to make the formula look like this, I have to take AP and I can take AB here. PB is also correct, but I can take AB here just to make the formula look like this. You can do it with PB also. So if this was instead of PB, I was AB vector, it is still coplanar. We can write it as B minus A and C are coplanar. So how do I write the condition for coplanarity? I would say R minus A is equal to S times B minus A plus T times C. And now I can simplify and write it as R is equal to 1 minus SA plus SB plus TC. where T and C are scalars. T and S are scalars, right? So technically, we have seen two cases so far. Vector through vector equation of a plane, through one point A parallel to B and C. In that case, my equation was R is equal to, we got A plus SB plus TC. And the second form we saw was vector equation of a plane through 2 points A and B parallel to vector C. In this case, I got the equation as R is equal to 1 minus SA plus SB plus TC, right? So both are coming from the same idea of getting three vectors which are coplanar, right? And now the third case that I will see is vector equation of a plane through 3 points A, B, and C. Through 3 points A, B, and C, right? So let's see what the equation comes in this case, right? That is the last case that we'll be considering. So if there are 3 points A, B, and C, A, B, C, let's make a variable point P in the plane, and we can say that AP vector and AB vector and AC vector are all coplanar. AP, AB, AC. These three vectors are coplanar, and therefore I can write AP vector as S times AB vector plus T times AC vector, right? And now we can rewrite this like this: R minus A is equal to S times B minus A plus T times C minus A, right? So simplifying this, what you will end up getting is R vector is equal to 1 minus S minus T A vector plus S times B vector plus T times SC vector. So that becomes the equation of a plane passing through three given points. So we have seen all the cases. We have seen plane through one given point parallel to two vectors, plane through two given points parallel to one vector, and also plane through three given points. And in all cases, we were able to write the equation of the plane in vector form by using the coplanar idea. Anytime you have points in a plane, you can consider a general point P on the plane and make vectors AP and AB and so on, which are coplanar with each other. So that is the theory that I wanted to discuss today. In the next class, I'll be doing some problems on the concepts that we have done so far. So next class will not be new theory. We'll do more problems and we'll revise everything that we have done so far. And after that, we'll continue with the further theory. The next theory class for vectors will be on dot products and cross products and product of vectors basically. So for now, just make sure that you revise through the first video and this video. And then next class, we'll do some more problems on these ideas. If you haven't subscribed to the channel, please subscribe. And if you like the content, please share it with your friends, like the videos. All your support is super important for me, and you will help the channel grow further and reach more students. So please do subscribe to the channel if you're watching the content. That's all I ask. Thank you. I'll see you next time.